which I couldn't complete last time. It was on rolling motion, and then we'll proceed with the review. But this part is part of your exam. You might be tested on rolling friction. Okay. Okay. So last time what I did was I did a problem on a ring. I believe it was a ring which was a force was applied to the ring, and I asked you to analyze the motion. In that case, what we did was we first assumed that it is rolling. We got a violation of the friction constraint. So then we knew that it was not rolling, it was sliding, and we proceeded solving the problem, right? Now this is a slightly different problem, okay? Let's read the problem, and then I'll tell you why it is different. So a force of 10 newtons is applied to a 10 kilogram ring as shown. If slipping does not occur, okay, you're told that slipping does not occur, find the ring's initial angular acceleration and the acceleration of the mass center g. Neglect the thickness of the ring. So in this problem, you are told that it is rolling, okay? So that constraint, or rolling constraint, is valid. You do not have to check for friction. In fact, you're not even told the coefficient of static and kinetic friction for this problem. You were told that for the previous problem I did in the last class. Okay, so as usual, we will start with a free body diagram. Okay, so since the ring is on a flat panel, there is a normal force. The external force is applied at, say, 45 degrees. Okay. However, I need to change this a bit. So the force is applied at 45 degrees, but the point of contact, so this thing makes an angle of 30 degrees. So this is 45 and this is 30 degrees. Okay, so this is F. What else? There's a force due to gravity. And then what else? Is that all? Friction. So there has to be friction force. Otherwise, it's good to assume friction unless you're told there's no friction. So friction, as I pointed out in the earlier class, acts in a direction which is opposite to the direction of motion. In this case, the force causes the ring to move to your right. So the friction force is going to act in the opposite direction. Okay, so I think that's about it. Okay, so we are asked to find, we are interested in finding acceleration of g and alpha. Okay, so let's resort to equations of motion. Okay, now this is a case of general planar motion. So there are three equations in general for rigid body. Planar rigid body means there are three equations. There is force equilibrium in the x direction, force equilibrium in the y direction, and then there is the moment equation. Now the moment can be taken about any point. It can be the center of gravity, g, or it could be really any point on the disk or outside the disk. It doesn't have to be on the disk. Okay. Now a judicious choice for the point is where maximum number of forces pass through. Okay. So in this case, maximum number of unknown forces, if you like. So in this case, you could take G, which is here. Okay. if you take G, then what happens is the force F acts, well, force F is known, so let's not bother about that. Let's look at N and F. N passes through G, okay, but FF does not pass through G. So when you do that, if you do equilibrium about G, then this thing will have an FF appearing in it, and FF is something which we do not care about. We are not interested in FF, right? You're asked to find acceleration. So what about choosing this point? So if you choose this point, it's called C here, right? Then you notice that N passes through C, FF passes through C, which means that when you do MC, those forces, the unknown forces N and FF, will not come in the equation. So it makes more sense to do moment equilibrium about point C. Okay, and for these problems, you'll see that it's much better to start with the moment equation. Even though when I wrote the equations, I wrote Fx, Fy, and M. It's best to start with M, and then try to go for Fx and Fy. So let's start with MC. Okay, so MC equals, so this is from the formula sheet, is equal to Ig alpha plus R G with respect to C crossed with mass times acceleration of G. And so as I said, this is sort of an abuse of notation. What I have here is a scalar equation. What I have here looks like a scalar equation, but here this is a vector equation, right? And really, the reason I wrote it that way is because you have to just interpret this as a scalar eventually. Interpret as a scalar, okay? So you take the cross product and you see that the cross product will be either minus k or plus, in the plus k direction, which is upwards, okay, or it could be minus k. So to ignore the k, because you're only interested in the scalar part of the equation. Okay, so let's start expanding this equation out. So the moment about C, so N, FF, and mg also passes through C. So those three forces will not come in the force equilibrium. The only force which will come is capital F, which is given to us. So F cosine of 45 degrees, this force acts in the x direction, right? X and y. So F cosine 45 x in the x direction. So what I need to do then is find the distance from C all the way to the point where F is applied, and I want the y distance, because when I find the moment, I need the force times the perpendicular distance to the point C. So this distance. So what's that distance? So the radius is 0.4, right? So it's 0.4 so 0.4 plus this distance. What's this distance? 0.4 sine 30 degrees, because this distance is 0.4 times sine of the angle. So this thing here is going to be 0.4 sine of 30 degrees. What about the sine? How does that moment act? Clockwise or anti-clockwise direction? Clockwise. So the reason why it's clockwise is F cos 45 is in the x direction. The radius r, well, the distance is that, and so the effect of F is to move this thing, if you hold the ring fixed about G, then the effect of F is to roll the ring in the clockwise direction. So clockwise, so if I curl my fingers along the clockwise direction, then my thumb gives me the direction of the moment. So that my thumb points in the minus k direction, so that's negative, or it's in the clockwise direction. plus f sine of 45 degrees. So f sine of 45 is acting in the vertical direction. Okay, so in this case, I'm interested in the horizontal distance, this distance. So what's this distance? 0.4 cosine of 30 degrees. So it's this distance, which is 0.4 cosine of 30. So f sine 45 times 0.4 cosine of 30 degrees. Okay. Well, I just put a plus sign. What's the sign? It's positive because f sine 45 acts upwards. We hold the ring at G. Then this force will spin the ring in the counterclockwise direction. This way, my thumb points in the K direction, which is positive. So this is equal to Ig times alpha. Ig times alpha. Now, alpha by default is assumed to be in the positive direction is counterclockwise. Okay. Now you have a choice here. You could either assume alpha to be counterclockwise or to be clockwise. Okay. If you choose it to be counterclockwise, it will be positive, and then when you do the math, it will actually come out to be negative. All you could do is you could just say that alpha, my alpha is going to be in this problem going to be clockwise, and so I put a minus alpha. Okay. It doesn't matter. You can assume either way. Your final answer will give you the right sign. Okay, so that's Ig alpha plus the moment due to this vector. So acceleration G is the acceleration of the center of mass, which is going to be on the right side. Now, if you assume that the ring spins clockwise, then clearly Ag is going to be in the positive x direction. Okay, so mass times Ag is a vector in the positive x direction. The vector Rg to C is a vector which goes from C to G. Okay, so it goes from bottom to top. Okay, so it's really, if you want to think of it, you could take the cross product there. So Rg comma C is, so one way to do this is to say this R is R times J crossed with mass times Ag, which is a scalar now, times I, and then you'll get MAGR. J cross I is, what's J cross I? Is negative K. So it's negative K. Okay, this is just one way to do it. If you think this is hard, I'll show you another way to do this. You can sort of visualize this. Mass times Ag is a vector which points in the x direction, and you want to take moments about point C because this thing is a moment about point C. So what's the effect of mass times Ag, a force in this direction, on the ring if you hold it fixed at C? It'll tend to spin the ring in the clockwise direction, right? If you have a, imagine this is the ring, and the force MAG is this way, and C is this point. If you hold the ring fixed at C and you take the moment due to this force, that force will tend to spin this thing in the clockwise direction. So this force causes a clockwise moment. So this is going to be minus mass times acceleration of G times R. Okay, you get the same thing if you use vectors. Okay, it's up to you. You can use vectors or you can just use it, use a pictorial way of doing this. So again, the reason why Ag is on the right is because you have to be careful here, which is if you assume alpha to be clockwise, then Ag would be to the right. If on the other hand, I'd assume alpha to be counterclockwise, that I put a positive sign here, then Ag would be to the left and it will produce a positive moment. Okay, both this, it'll either be positive positive or it'll be negative negative. So you have to be consistent across Ag and alpha, but you can assume any sign for alpha and Ag. If you fix the sign for alpha, it fixes the sign for Ag, and vice versa. Okay, so in this equation, F is known, so F is given, the mass is given, the radius is given, so F is given, Ig, well, Ig for a ring is mass times r square. Since mass is given and the radius is given, that is known. Okay, what's unknown? So this is a single equation where there's an equal to sign here. This is a single equation with two unknowns, alpha and Ag. Okay, so we cannot solve for Ag and alpha using one equation because it's one equation, two unknowns. So we need one more equation. So my question to you is, what is that equation? When a disk is rolling or a ring is rolling, what's the relation between acceleration and angular acceleration, linear acceleration, angular acceleration? So for pure rolling, Ag is equal to R alpha. Okay, this is always true. So this is equation 2. So what we have here effectively is equations are 1 and 2, unknowns are Ag and alpha. So we can solve for those two unknowns. So I'll leave it to you as an exercise. By the way, this I should have written it this way. This is kinematics. Okay, so solving, we have Ag equals 0.224 meters per second square and alpha equals 0.56 radians per second square. Okay, now my question to you is, I solved for Ag and alpha. If I asked you to find the friction force and normal force, what would you do? So we have only used one equation. We've still not used two equations. One is the force equilibrium in the x direction, force equilibrium in the y direction. You can use those two equations. So there'll be two equations, and there'll be exactly two unknowns, SF and N, and you can solve for those two unknowns. Any questions on this? Okay, so the rod OA rotates with a constant angular velocity of theta dot. The ball rests on a frictionless surface, so this is frictionless. As shown, the ball is in contact with the rod and the rod pushes the ball to the right. So if you want to visualize this, the rod is turning at a constant speed, clockwise direction. In the process of moving in the clockwise direction, it tends to push the ball to the right. And the ball is on a surface with no friction. Draw the free body diagram of the ball and outline a procedure to solve for all external forces acting on the ball. Okay, so first of all, you know that it's going to be chapter 13 or 17. Now my question to you is this a particle problem or it's a rigid body, planar rigid body motion problem? Particle. It's a particle problem because I've not given you the inertia. So there are hints in the problem. I've not given you inertia, so it cannot be a rigid body problem. So you want to guess this thing. Sometimes there's a hint, sometimes there's no hint. But unless you know that, you will not know which equations to use. So free body diagram, okay, of the ball. So let's draw the ball. Okay, now the ball is in contact with the surface. So the moment I remove the surface from the ball, I have to replace the effect of the surface on the ball with a force. Okay, so that force is going to be clearly in the normal direction. Let's call this n. Let's say n1. Okay, there is no friction force, so I don't need to put any friction force there. The rod rests against the ball or the particle, right? And in my free body diagram, I have only the ball. There is no rod, right? So I have to replace the effect of that rod with the force, and that force again is going to be normal to this. So N2. Okay, is that it? What's that? The weight of the ball. So just G. If I don't give you G, feel free to assume there's no gravity. You make your life easy. Okay, now here's the thing. For a particle, it's absolutely fine to show the forces wherever you want because there is no rotation. However, for a rigid body, I will not show the force like mg, I will not show it like this. I'll show it exactly where it acts. Because when you do the moments, it's very important to know where the force acts. For a particle, that's not true. Okay, so those are the forces. What's the next question? Outline a procedure to solve for all external forces acting on the ball. So since the question is find the forces, obviously I have to use kinetics, which is Newton's laws. Before I use Newton's laws, what do I do before I use Newton's laws? Equations of motion. But before I write the equations of motion, how do I write the equations of motion? They need to be inserted in the frame of reference. What's the frame? What would I use? Cartesian? Tangential. Okay. There are only three answers, right? You can guess what's the right answer. What's there in the problem which tells you what frame to use? There's r and theta, so it's clearly cylindrical coordinates, r and theta. So this vector, this line here, vector, is along the r direction, and then I'll call it ur, and theta, u theta is going to be in the direction in which theta is increasing. So theta is increasing in this direction, right? Theta would be increasing that direction. So u theta. Okay, so once we have that, now we can write the equations of motion, because equations of motion requires acceleration, and I better know the frame of reference when I write the acceleration. Okay, so Fr is mass times acceleration in the r direction. So net force in the r direction is okay, so N1 and mg act in the vertical direction, so those forces will contribute to ur, and N2 acts in the theta direction, so that will not contribute. So N1, and really if this is theta, then this has to be theta. So N1 cosine theta acts along ur, and it's in the positive ur direction, right? This force, when you resolve it along this, it's going to act in the positive ur direction. Mg, on the other hand, acts in the direction opposite to N1, so it's going to be negative mg cosine of theta. So that's about it. Those are the forces in the r direction, external forces. So this is equal to mass times acceleration in the r direction, which is r double dot minus r theta dot square. Okay, and then the next equation is f theta is mass times acceleration in theta direction. So N2 acts along positive u theta, so that's positive N2. and N1 and Ng act at an angle to theta. So it's going to be this angles. This is 90 minus theta because UR is this way, U theta is along this. So the angle between R and theta is 90, and so this has to be 90 minus theta. So N1 acts along negative. So N1 when resolved in U theta direction acts in the negative U theta direction. So it's N1 cosine of 90 minus theta, which is sine of theta. And Mg has to also to be resolved in the U theta direction. That's going to act in the positive U theta. It's going to act exactly opposite to N1. So plus Mg sine theta equals mass times R theta double dot plus 2R dot theta dot. Okay, that's the acceleration formula. It's in the formula sheet. Okay, so the question is, I need to find N1 and N2, right? So these are two equations, okay? I need to convince myself that these are two equations in two unknowns. And if that's true, then I can solve those two unknowns using the two equations. So everything else has to be known. So let's see what are the things we know. Well, theta will be given to you, so that's known. Gravity is given, mass is given. I still need to compute R and theta, theta dot, and theta double dot. So let's see if we can compute R, theta, and theta dot. So R and, oh, I think, okay, so, my bad. This should have been, what is this, D. Okay, so that's D. My bad. It should be the point from 0 all the way to the point where I've shown R. So I can use the fact that R cosine theta, this distance is D. So R cosine theta is D, right? And D is given to me. So I can write R equals D secant theta. Okay, and then I know what I can find R dot, R double dot, right? I can find that theta is given, theta dot is given, theta double dot is, what's theta double dot? 0. It's moving with constant speed, so that's 0. So I could solve R for R dot given D and theta dot and theta double dot. So in effect, what I've done is effectively shown that I can solve this for this and I can solve for this. All those things are unknown. So what I'm left with is two equations, two unknowns, and I can solve it. Okay, so there are 4 more problems in this. I'm going to post solutions to